So we just did section 3.1 where we talked about the Bernoulli and really the binomial random variables. Okay, chapter 3 is just full of different discrete random distributions. Okay. We're only going to do sections 3.1 and 3.2, okay, as far as what I'll actually have you do homework on. And then there's one video for the Poisson distribution because it's still common enough you might see it in another class somewhere. But really, once you learn how to do one distribution, after that it just becomes a matter of being able to have someone give you a formula and then you know how to use the formula. And just to note that different textbooks use different definitions of these distributions, and so their formulas might look different. It all comes down to the same thing. It's just what kind of letters and symbols you're using. So first, let's do the geometric distribution. So we use the geometric distribution when we have a sequence of independent trials. So far that sounds like the binomial, right? Each trial has either success or failure. That sounds like binomial as well. Okay. There's a constant probability of success, P. That sounds like binomial. Okay. We are interested in how many trials we need to get our first success. Now this is different from the binomial. The binomial tells us we know we're doing the trial n times and we count our successes. What is the geometric saying? The geometric says how many trials we need to get our first success. So this is how it differs from binomial. Everything else is exactly the same, but instead of knowing you're doing something, say 10 times, you say how many times do I have to do it to get one success. So again, geometric, X is the number of trials up to including the first success. That's how you know it's geometric. They'll say first success. Okay, so what would be your possible X values? Well, X could be 1, 2, 3, and there is no upper limit because you don't have a place where you know you're stopping. You go until you get a success. Okay. But they do have the nice formulas for us. We're not going to take time to find them. We'll just say here they are. So the probability that x equals x is 1 minus p to the x minus 1 times p. This is very logical still. This is the probability of failure. And then you have to fail x minus 1 times. And then finally you get probability of success. So if you think about how we did our probabilities, basically you'd be saying, okay, the first thing has to be a failure, so I do 1 minus p, times the next one has to fail, so times 1 minus p, times the next one has to fail, so times 1 minus p. And you do that all the way up until the very last time when you suddenly get a success, and so you times it by the probability of success. So this is our PMF. Okay, and then they give us our CDF. So the probability that x is less than or equal to some number is 1 minus p to the power of x. So that's actually really nice to have our CDF formula, because it means you don't have to find each probability one at a time, like we did for the binomial. The expected value and variance, expected value is 1 over p, and variance is 1 minus p over p squared. Let's try it out. So suppose you decide to roll a fair die until you roll a 1. Okay. So that kind of until you roll a 1, that's telling you it's going to be geometric. You want your first success. Let x be the number of times you have to roll the die. So this would be geometric. And p is going to be what? What's the probability of getting a 1? Probability would be 1/6, right? They didn't say 6-sided die, but if they don't say otherwise, it's always a 6-sided die. So first, what would be your PMF? So probability that x equals some specific number. The general formula is 1 minus p to the power of x minus 1 times p. So in our situation, 1 minus 1/6 will be 5/6 to the x minus 1 times 1/6. And so that's going to be our PMF. And if you wanted to find the CDF, probability that x is less than or equal to some specific value. The general formula was 1 minus p to the x. So in our case, it'll be 1 minus 1/6 is 5/6 to the power of x. So we know our PMF, because it's a probability mass function, and we know our CDF. These are nice now, so we can find probabilities in part 3. So let's find the probability that we roll the dice exactly 5 times. So that's saying find the probability that x equals 5. So all we have to do is plug 5 into this PMF here. So plug 5 into the PMF. So here we'll use the PMF. So it says it's 5/6 to the power of x minus 1, so 5 minus 1, times 1/6. So 0.0803. So about an 8% chance you have to roll it 5 times. Let's find the probability now that we roll the dice between 3 and 7 times, and we want to include the 3 and the 7. So this one, you kind of have to think a little bit. You don't have to find each probability one at a time, but you could, actually. And it might be the easier way for you to do it if you have trouble. Okay, because I could do the probability that x equals 3 and 4 and 5, plug them all in PMF one at a time. But let's try and use our CDF. So we want the die to be between 3 and 7, so really we're saying probability that x equals 3, or 4, or 5, or 6, or 7. Let's see. So I want to do the CDF because I have more than one probability I'm interested in. So I might start by finding the probability that x is less than or equal to 7. Okay, but what's that going to do? That's going to give me from 7 all the way down. But I only want from 7 to 3. So what would I do here? So let's wait a second for any thoughts.
Subtract the probability of x is equal or greater than 2.
Okay.
2.
So we'll do probability still that x is less than or equal to 2, because that would take out my 0, my 1, and my 2. Okay. So x is less than or equal to 2 here. We'll subtract out that probability. Now, I didn't write this up above. I should have. Let's write up above. This is capital F of x is our CDF. So capital F of x is the probability that x is less than or equal to x. So this x less than or equal to 7, that looks like the definition of the CDF. And x less than or equal to 2, that's also our CDF. So we can say that's really just f of 7 minus f of 2. So all I have to do is plug 7 into that formula and then plug 2 in. So let's do the 7 first. So 1 minus 5/6 to the power of 7 minus, and then we'll do 1 minus 5/6 to the power of 3. So this is the CDF at 7. Oh, not a 3. 2. And the CDF at 2. So this gives me 0.415. So I could have done 3 or 4 or 5 or 6 or 7, but that's 7 different things I have to plug into the PMF. Plugging 2 things into the CDF is a little bit easier to save time. Okay, now find the expected value of x. All we have to do is look at our formula. Expected value of x, I said our formula is always just going to be 1 over p. So just 1 over p is 1/6, so 1 over 1/6 is 6. Okay. That kind of makes sense, right? How many times might we expect to have to roll the die until we get a 1? It turns out that the expected value, or the average number of times, is 6. So let's just make ourselves a little bit of a note here. This is the average. It's the average number of times we have to roll the die to get our first one. And that's what expected value is. Remember, it's kind of what you expect to have to do, or how many, or the average. Okay, so we expect we'll have to roll about 6 times to get our first one. Sometimes it'll be faster, sometimes it will be longer. But the average is about 6 times. And the variance is 1 minus p over p squared. So 1 minus 1/6 over 1/6 squared gives me 30. Let's try another one. So in this example, now we decide to flip it for a coin until we get ahead. Let's let x be the number of times we have to flip the coin. Okay, so notice we are until we get ahead. So we are interested in first head. So x is the number of times we have to flip the coin. So because you know you're interested in that first head, that tells you it's going to be a geometric. Okay, and we're tossing a coin, so we have a 1/2 chance of getting a head. Okay. So p is 1/2 because the probability of heads is 1/2. Now you should always write down what x is, although sometimes it's saying it up in the sentence, so I haven't written it down, but x is number of attempts to get the first head. So you can see over here I have done a nice little graph for you. So in my first graph we have x on the x-axis, and over here we have the probability. So this over here, my top one, is my PMF because it's telling me the probability that x equals a specific value, or the probability. And then this table here, the actual table, so these are separate, the table is my CDF because it tells me the probability that x is less than or equal to some specific value. So you can kind of see it's pretty likely that I would have to do it 1 time, less likely that I have to do it 2 times, less likely, and then it gets pretty unlikely as you go up, because if you have a 1/2 chance of getting a head, you should get one fairly quickly. Okay, first, what would be the PMF? So the probability that x equals our specific value. Okay, remember our formula, 1 minus p to the x minus 1 times p. So in our case, 1 minus 1/2 to the x minus 1 times 1/2. And that actually simplifies. 1 minus 1/2 is just 1/2, so we have 1/2 times 1/2, so we just have 1/2 to the power of x. And that's just because in this one situation, 1 minus 1/2 gives us 1/2. And to find our CDF, probability that x is less than or equal to our specific value, it's going to be 1 minus p to the x. So 1 minus 1/2 to the x gives me 1 minus 1/2 to the power of x. So now, number 3, let's find the probability that x is less than or equal to 3. There are different ways you could do this. You could use the PMF or the CDF. Let's do both just as kind of that little refresher of how you could do it both ways. So probability that x is less than or equal to 3, if you want to use the PMF, is you'd have to say what's the probability that x equals 1 plus the probability that x equals 2 plus the probability that x equals 3. Notice we don't have zeros because if you're trying to get your first attempt, you have to do it at least 1 time. Okay. Now you could plug this into your formula, or we could come back up and look at our chart. So just looking at our chart, for x equals 1, the probability is 1/2, then 1/4, then 1/8. So look at graph. So we get 1/2 plus 1/4 plus 1/8 gives me 0.875. And for our CDF, we just do straight up probability that x is less than or equal to 3. You could look up at your chart, or you could just plug it into your CDF, just plug 3 into your CDF. So 1 minus 1/2 to the power of 3 just gives me 0.875. I just realized this 1/2 to the x, you should probably put parentheses around that, huh? We don't want it to just be 1 to the power of x. We want it to be 1/2 to the power of x. So our CDF and PMF, these are fairly simple to plug it in. Okay, but notice the CDF saves you time. You don't have to do 3 different values. Number 4, let's find the probability that we have to flip it more than 7 times. So again, usually on these I sometimes have to stop and think about it. So what are our possibilities? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, ... But notice it doesn't stop, does it? And so if I wanted to find the probability that I have to do it more than 7 times, I'd have to do the 8 and the 9 and the 10 and the 11. So we're looking for the probability that x is greater than 7. And so I'd have to do 8, 9, 10, 11. But I don't actually know where to stop. So I would just have to keep putting them in my calculator forever and ever. You don't want to do that, right? So instead, let's use the complement rule and do everything that's left. So complement rule is this is going to be 1 minus the probability that x is less than or equal to 7. Now you could find the probability for 1 and 2 and 3 and 4 and add them all up. Or let's just use our CDF. So 1 minus that x less than or equal to 7, that's just the CDF at 7. So 1 minus, now the entire CDF, so we get a lot of 1 minuses because the CDF is 1 minus 1/2 to the power of x. So 1 minus 1/2 to the power of 7. So 1 minus the entire quantity, 1 minus 1/2 to the power of 7, gives me 0.0078125. Find the expected value of x. So expected value of x is 1 over p. So 1 over 1/2 gives me 2. And the variance of x is 1 minus p over p squared. So 1 minus 1/2 over 1/2 squared gives me 2. And this is just one of those weird coincidences where the expected value and variance are the same. Really quick. So the this next one is called the negative binomial distribution. And we use the negative binomial distribution when we have a sequence of independent trials. Each trial is either a success or failure. And you have a constant probability of success, p. And now here's the thing that sets it apart from the others. We use it when we're interested in how many trials we need to get our rth success. So again, this key thing here is it's how many until you get r successes. So it's actually very similar to the geometric. I've never quite figured out why they call it the negative binomial and not something like negative geometric. But it's probably because our actual formula looks very similar to the binomial. So what we'll do is we'll say x is our number of trials up to including the r success. So your possible x values are r plus 1 up to r plus 2, etc. Because if you want r successes, you have to do it at least r times. So our PMF is the probability that x equals little x is going to be x minus 1 over choose r minus 1. So that's a combination there. And then we're going to do p to the r, 1 minus p to the x minus r. Okay. Because we need r successes, but we also had to fail all those times up until we got r successes. So we had x minus r failures. Let's see. Our expected value and variance are r over p for expected value and r times 1 minus p over p squared for variance. So let's say in this example we decide to toss a fair coin until we get to the second head. So in this case, r would be 2 because we want to get 2 successes, and our probability would be 0.5 because we're just tossing a coin, so we have 1/2 chance of getting a head. So it's kind of big here, but you can see here's my x's, here's my probability. So this is my PMF, or the probability that x equals x. And then down below, separately, you have a table. so for each x value, and then you have the probability that x is less than or equal to that. So all of the x's up to each value. So like this one is the probability that x would be less than or equal to 8 is 0.965. So we toss a fair coin until we get a second head. We could find the probability that we have to toss it 6 times. So remember, it's not n, but x minus 1. I might have the binomial one memorized. I do not have this one memorized. We never use it. Or it's not nearly as common, I should say. We still use it. But x minus 1, so probability that x equals x is x minus 1, r minus 1, p to the r, 1 minus p to the x minus r. So we want to toss the fair coin until we get the second head. So that means we want to get 2 successes. So r equals 2. And the probability of getting any head is 1/2. So now you just plug it in. And so in this case, toss the coin 6 times. That means x equals 6. So we'll do 6 minus 1, 2 minus 1, 1/2 to the power of 2, and 1 minus 1/2 to the power of 6 minus 1, which is 0.0781. So what I want you to remember on these is it's not important that you leave this class having memorized all of the different distributions. What is important is that if I say this is negative binomial and here's the formula, could you go through and plug stuff in? Okay. Or find the expected value. That's really easy because they give us the formula. It's just r over p. So r is 2, p is 1/2, so 4. So we expect if we want to get 2 heads, we'll have to toss it about 4 times. Okay. And if you wanted to find the variance, it's just r times 1 minus p over p squared. So we'll have 2 times 1 minus 1/2 over 1/2 squared, which gives me, well, 4 as well. That 1/2 just throws everything off. And then, if you want to find the standard deviation is just the square root of that, so 2. So in this next example, Bob is a high school basketball player. He's a 70% free throw shooter. This means his probability of making a free throw is 0.7. We are interested in how many shots it takes him to make 3 free throws. So we're interested in x equals the number of shots until 3 successes. Okay, and because it's how many times you have to do it until you get 3 successes, we know that's negative binomial. And r equals 3, we want 3 successes, and each probability, the probability of each one is 0.7. So what's the probability that it takes him 5 shots? So probability that x equals 5, is we're going to plug it into our formula. Our formula is x minus 1 over r, sorry, I keep saying over, that's a choose. So x minus 1 choose r minus 1 times p to the r times 1 minus p to the x minus r. Okay, so in our case it's going to be, see, 5 shots, so x equals 5 is 5 minus 1, and r is 3, so 3 minus 1. Probability is 0.7, and we want 3 successes, and then we want 1 minus 0.7 is the probability of failure, and we want r minus 3. Sorry, x minus r. X is 5. We did it 5 times. We want 3 successes. That means you'd have 2 failures, or 5 minus 3 failures. And this is 0.18522. So what's the probability that it takes more than 5 shots? So if you were to label this out, he could have, actually, we don't start at 1, do we? If we want at least 3 successes, we start at 3, 4, 5, 6, 7, 8, 9, but there's no upper limit, right? We just have to keep going. So if we say more than 5 shots, we'd have, let's see, more than 5 doesn't include 5. We'd have to do the 6, 7, 8, 9, 10, but we'd have to keep going, and you would never be able to stop. You'd just be finding probabilities forever. So we don't want to do that. Let's use the complement rule. So the probability that x is greater than 5 is equal to 1 minus the probability that x is less than or equal to 5. So we want this less than or equal to 5, which is really just the 3, 4, 5. So it's going to be 1 minus, we'll do the probability that x equals 3, plus the probability that x equals 4, plus the probability that x equals 5. So 1 minus. So the probability of 3, all we have to do is just plug the 3 into the PDF up here, or PMF. So we'll do 3 minus 1, and r is also 3. We'll do 0.7 to the r of 3, and 1 minus 0.7 to the x, which is 3, minus r, which is also 3. Plus, and now we'll do the x equals 4, so we'll do 4 minus 1, which is 3 minus 1, 0.7 to the 3, and 1 minus 0.7 to the 4 minus 3. Plus, and then for the 5, we already did that, so let's not duplicate our work, so 0.1522. So you put all of this in your calculator and you get 0.16308. Oh, and right here I didn't say, but the probability that x is greater than 5 is equal to 1 minus the probability that x is less than or equal to 5. That is the complement rule. So we'll just make a little note here, complement rule. Let's see, number 3 now. What's the expected number of times he has to shoot before he can make 3 free throws? Well, expected value is really easy. We just find our formula for a negative binomial is r over p. So r is 3, p is 0.7, so we get 4.28. So on average, he'll have to shoot a little more than 4 times to make 3 free throws. And what's the standard deviation? Well, anytime you ask for standard deviation, find variance first. Variance is r times 1 minus p over p squared. So we'll do 3 times 1 minus 0.7 over 0.7 squared is 1.836. And our standard deviation is the square root of variance, which is the square root of 1.836, or 1.354. So there's your standard deviation.